Hello, good afternoon. I have with me our textbook. Okay, I have the hard copy, and you have the electronic copy, the soft copy. Okay. Let me have some discussions of some problems. Okay, because I still believe that you need some coaching. Although the problems are just utilizing the ordinary equations so far we discussed. Okay? Now this time, it's a combination of the three laws of motion. Now, chapter 5 is telling us that in nature, in the physical nature, there are laws of nature that govern the behavior of a physical body. Okay? We are physical bodies. The human body is a physical body. We are also governed with the laws of physics. Remember, my dear students, that laws in physics are laws of nature. Okay. Now the first law is telling us, the first law as formulated by Isaac Newton, telling us that in the absence of a net force, or a resultant force, or an unbalanced external force, a body at rest remains at rest. So, if you are inside your house, you have tables there, you have the cabinets, the apparatus, the chairs, they are at rest, and they will remain at rest in the absence of an external unbalanced force. There are forces acting on the chair right now. There are forces acting on the table right now. The forces acting on the chair, a single chair. There is that force that makes the chair remain in contact with the surface of the floor, and that force is the force of gravity, and we ordinarily call that the weight of the chair. The chair has weight because anything on the surface of the earth is acted on by the force of gravity of the planet Earth. And this force of gravity is directed toward the center of the earth, the center of the earth. You have a weight, and that weight is equivalent to the pull of gravity of the planet Earth against you. If you and me and all of us are in the outer space, far, far from the planets and other objects in the solar system, in the universe. In other words, we are isolated. Then, ladies and gentlemen, we are, or we will be in the state of weightlessness. State of weightlessness. We are weightless. So, if you are weightless, I am weightless. Suppose I would like to urinate, because that is one of the, well, characteristic of a human being, able to urinate. In the outer space, how can we urinate? How can we defecate? Maliban. How can we defecate? when our stool or our urine are also weightless. You just imagine that life there in the outer space, isolated from all objects in the universe, from all planets, meteors, comets, asteroids. We are isolated, and so therefore we will be again in the state of weightlessness. So in this problem, as governed by the three laws of motion, we always have what we call forces. In the case of the chair, there is that force coming from the pull of gravity. That's why it is in contact with the surface. It is free to move, but it is in contact on the surface of the earth. You can pull that up, but if you are going to release that chair, the chair will move down to the surface and will be in contact in the surface, and while there, it remains at rest in the absence of a net force. There are forces, but all the forces balance each other. What are these forces? The force coming from the pull of gravity, your weight, and the force exerted by the surface against that chair. And that force on the surface exerted by the surface against the chair as the object on the surface is what we call the normal force. So in chapter 5, there are a lot of illustrations about the normal force. There is that problem there. As example of chapter 5, a person on the elevator. And while the elevator moves up, the normal force there will be greater than the weight. Okay? The normal force there will be greater than the weight. In other words, if you want to get your weight, you will have an overweight there because of the motion going up. You're pushing down the floor of the elevator. The normal force there reacts. Okay, here. Number 1. According to the Guinness Book of Records, the heaviest man ever had a confirmed mass is 975 pounds. This is conversion, a continuation of chapter 1, conversion from pounds to kilograms. Okay. So you are going to convert that. You are going to show the conversion. Okay. You are going to have something like this. You have 975 pounds. 975 pounds. Multiply that by 1 kilogram per 2.205 pounds. So you cancel that out and you have the answer. You have the answer in kilogram. But you are going to draw a man, A man. You're going to draw a man. Okay? So you have here the man, example, just a stick man, okay? There is the weighing scale here. There is the weighing scale. On top of the weighing scale, and there is the weight registered, 975 pounds. And suppose that weighing scale is in terms of kilograms, then you would expect the measurement in kilograms. And the value is no longer 975, the numerical value. Okay, it will be smaller than 975. Okay, then number 2 here, number 2. The hydrogen atom consists of 1 proton and 1 electron. What is the mass of one hydrogen atom? Then you have there C table 5.2. So I wrote here the table 5.2 so that you don't need to go to the pages there, scan the pages where the pages are. You are going to look for the pages. What page is table 5.2? No problem, my dear students. I am providing you table 5.2. Now in table 5.2, you have, because the problem is about the hydrogen atom, so you drew the hydrogen atom. This is number 1. Number 2, hydrogen atom, so you will have here hydrogen atom. Okay. Hydrogen atom is thought to be spherical in form, shape, and size. Spherical. Okay? Of course, no one has seen an atom, and no one will ever see an atom in the future of the future. No one will see an atom forever. You cannot directly see an atom because an atom is very, very small. Very small. How small? How small? Have you seen a needle? The needle, the one used by the dressmaker to sew your clothes, your dress, needle. You have seen it? I have seen it. You must have seen one also. The tip of the needle, that's the smallest part of the needle. The tip of the needle is the smallest part of the needle. At the tip of the needle, there are millions of atoms. That is how small an atom is. If the size of every human being, if the size of every human being is equal to the size of the atom, there will be no overpopulation because you can put even a billion of human beings at the tip of the needle if the size of every human being equals the size of an atom. So very small. Do not ask me, when can we see an atom? We cannot. When? We cannot. Now, atom, then it has electron and proton. So what is the mass of the atom? The mass of hydrogen atom, equals the mass of electron plus the mass of proton. So very easy, okay? Going back to the book. What is the mass of one? Okay. Then after solving it, you have that mass of, in other words, the mass of hydrogen atom is equal to the mass of electron plus the mass of proton. Combine them, there you are. That's the mass of hydrogen atom. Very small, because the mass of electron is 9.3 times 10 to the negative 31. 9.11. 9.11 times 10 to the negative 31. Negative 31, very, very small. Very, very small. So, it is mass of electron equals 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. Then, 9, 11 kilograms. Oh. Very small. Okay, very small. There are 30 zeros. There are 30 zeros after the decimal point. Very small. Okay. So, then you are going to add. And so, your answer will be still very, very small. Very less than 1 kilogram. In terms of grams, you will have 27 zeros. In terms of grams. So, mass of electron equals 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, then 9, 11 grams. Grams. Still very, very small. And 1 gram is about the mass of 1 plastic paper clip. 1 gram. I hope I have a paper clip here. Paper clip. I have a paper clip. Paper clip. I'm looking. Okay. This one is about 2 grams. About 2 grams. The smaller one is about 1 gram. But there is one that is lighter than this, bigger but lighter than this, about 1 gram. Okay. 0 something, very small. In terms of grams. Or if you imagine 1 gram of water is about 1 cc. 1 cc of water, 1 ml of water, that's 1 gram. So very small. Okay. Then the next question is, how many hydrogen atoms are there in 1 kilogram of hydrogen gas? So you are going to have conversions. 1 kilogram, okay, equals how many hydrogen atoms? So you have to have a conversion. So what is the answer here? What is the answer for this problem? The answer there is more or less about 1.67. Okay? More or less about 1.67. Let's see, approximately. Let me just have a calculator. Calculator. Electron, 9.11 times 10 to the exponent negative 31. Okay? Then plus proton 1.673 times 10 to the exponent negative 27. The answer is, this is the answer. Mass of hydrogen atom is equal to 1.673911 times 10 to the exponent negative 27 kilograms. Okay. Now, if you have if this is This is per 1 atom, per 1 hydrogen atom, per 1 atom. Okay? Per 1 hydrogen atom. Okay? 1 hydrogen atom has this mass. So you have a conversion. You are going to multiply this one. Okay? You are going to have this one. Something like this. For number 2, next question is 1 hydrogen atom, 1 hydrogen atom per, okay, 1.673911 times 10 to the negative 27 kilograms. Multiply that by 1 kilogram. Multiply that by 1 kilogram. So cancel the kilogram. The answer there would be, okay, the answer would be is equal to 5.974033267 times 10 to the exponent 26 hydrogen atoms. Okay? That is what I would expect in your computation, in your solution. Okay? Okay. And then, in the succeeding problems, you will be applying what we call the equation of force according to Newton. Here, you will have F equals ma. This is the classical force. This is the Newtonian force. Then, in succeeding problems, you will be finding this one in order to get for the force. Mass is given. And by the way, if mass is not given, you will have mass equals W over G. Weight over acceleration due to gravity. And this is equal to the weight equals M times G. Let us have some problems there. Okay. Number 3 problem, no problem because it's still similar to number 2. You just add all the masses of protons, neutrons, and electrons using table 5.2. Okay. What is the mass? No problem. The same process for number 2. The number 3, the same process as number 2. The number 4, boy and a girl engaged in a tug of war. Okay. Slippery. So, this condition of being slippery, the surface is telling us that there is no friction. If ever there is friction, such friction is negligible. So most likely they are having the tug of war on a snow surface. Then, while they are pulling on the rope, the instantaneous acceleration of the boy is given 7 meters per second squared. Toward the girl, there's a drawing. Okay, there's a drawing. Number 4 problem. And the instantaneous acceleration of the girl is 8.2 meters per second toward the boy. So, both the boy and the girl are moving on opposite directions against each other. Okay, toward the boy, the girl is, and the boy toward the girl. And then the acceleration of the girl given. Okay? Now, let us have the situation. I'm going to erase this one, erase. I'm going to erase this one, erase. So just review this one, this video review to understand. I'm going to erase. 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 Okay. Erase. It is now erased. I'm going to erase this also. Erase. Okay. Now, there is this boy. Okay. Then this is the boy, and you have here the girl. Pulling the rope. Okay. The boy moves in this direction. The girl moves in that direction. Okay? The boy is moving with an acceleration. There is that acceleration equal to, let me check the book. The acceleration of the boy is 7.0 meters per second squared. The acceleration of the girl is 8.2 meters per second squared. Okay. Then the boy has a mass of the boy. The mass of the boy is given to be 50 kilograms. 50 kilograms. The mass of the girl is equal to, we do not know. It's a question mark. And that is being asked by the problem. What is the mass of the girl? And so, we are going to have this equation. Okay. The force exerted by the boy on the girl is equal to, okay, the negative opposite of the force of the girl on the boy. And because we are asked of the magnitude, so we get the absolute value. Absolute value, magnitude. Let me check. Okay. Boy, the mass of boy, what is the mass of the girl? Okay. Instantaneous, so we get the magnitude. Okay? So you have here, based on the second law of motion, mass of the boy times the acceleration of the boy is equal to mass of the girl times the acceleration of the girl. Remember, our Newtonian force involved here is ma. So, in other words, F of the boy equals F of the girl. Okay? So, F equals ma. F equals ma. But we indicate the subscript for the mass of the boy, mass acceleration of the boy with letter B, referring to the boy. And we indicate the mass of the girl with letter G, capital letter G, and the acceleration of the girl with capital letter G. Sir, why not small letter G? Pwede, but you know, small letter G is usually or commonly denoting for acceleration due to gravity. It is commonly used. So to avoid the misinterpretation that we are using here, the G equivalent to the acceleration due to gravity, we better have another symbol. But actually, you can have that. Nobody can prevent you from doing that. How about the score, sir? Well, it's still correct if you correctly solve it. Okay? If you are not confused, then you can use any other symbol. Because all the symbolisms here, all the symbols here, depend on your choice. Your choice is as good as mine. Okay? Don't be bookish. You can invent your formula so long as that formula is consistent with the concept and principle. And you can justify it, defend it. Okay? Okay. The years to come, you must have your own formula in life. And that formula should be consistent with nature. It should not be against nature, but consistent with nature. Okay. So here, what is unknown here is, the one unknown here is this one. This is unknown. The mass of the girl. And so therefore, you're going to have the mass of the girl is equal to M of the boy, A of the boy over A of the girl. Everything is given. You can solve for the mass of the girl. Okay. Then, here. Very easy. Number 5. Very heavy book. This very heavy book. Number 5. On a flat road, a Maserati sports car. Oh, Maserati sports car. Very expensive car. Like a Ferrari, Mercedes, Mustang. A Maserati sports car can accelerate from 0 to 80 kilometers per hour in 5.8 seconds. Okay, the mass is given. What is the acceleration? So there is that. This is for number 3. No, this problem is number 5. So number 5 problem. Acceleration. Okay, given initial speed equals 0. Final speed is equal to given 80 kilometers per hour. Okay. 80 kilometers per hour. Okay. And the time it will take to accelerate, is 5.8 seconds. 5.8 seconds. Okay? Seconds. As the acceleration is being asked, V minus V sub 0 over T. We discussed this one in chapter 2. Accelerated motion. So, final speed given, initial speed given, time given. You can solve for the acceleration. Then after that, what is the force? Force equals MA. A here. M is given. M is given. Oh, the mass is given. The mass equals 1620 kilograms. That is the mass. That is the mass. Okay. Then you can solve for number 5. Number 6. For number 6, still, Okay? You are going to have the acceleration. What is the acceleration? Okay. First, you are going to get the mass, then get the force, you can have the acceleration. What is the acceleration? Okay. This is for number 6. Acceleration is equal to F over M. Acceleration equals F over M. F given. You look at the problem number 6. F is given. M given. The mass is given. You can solve for the acceleration. Okay? Okay. Then, number 7, what is the horizontal force? Okay? So, you are asked of the force also. Okay. Problem number 7. Driving the car with a seatbelt, seatbelt. Seatbelt. Then while driving the car, a collision happens. Pop! The car decelerates, meaning decreases speed until there is that collision. Maybe brakes were applied, but a collision happened. So, while driving 50 kilometers per hour, then BAM! Collision. The car stops from a speed of 50 kilometers per hour to 0 at rest. In a matter of, in this problem, 0.12 seconds. Let me check. 0.12 seconds, less than a second. So, you have to be extra careful, my dear students. When you are driving a vehicle, a car, a motorcycle, a single mistake will compromise your safety while driving. And the time involved there is very small. It is just a wink of an eye. Just a wink of an eye. 0.12 seconds. 0.12 seconds. Just a wink of an eye. Wink. What is a wink of an eye? I will let you see the wink of an eye. Ready? Get set. That's the wink of the eye. Ready? Wink of the eye, Ready? Get set. That's the wink of the eye. In other words, a very short time. So, you are asked, what is the force exerted on the seat belt? Because the seat belt here will prevent the driver from moving forward. The seat belt will prevent your body, if you are the driver, the seat belt prevents your body to move forward so that you will be just on your seat. Because in a collision, while you are moving very, very fast, according to the first law of motion, a body in motion will continue in motion. Just like when you are a passenger of a bus. Okay? You are at the back of the driver. Say while inside the passenger bus, the bus is moving, let us say 80 kilometers per hour. Now, while that bus is moving 80 kilometers per hour, somewhere over there, beyond and in front of the bus. Something to cross the road. Probably the one that crosses the road is a small pig. Small pig. What is the name of the small pig in your place? In our place in Dumaguete, we call that baktin. Baktin. And because the driver respects the animal right of the pig, and that right is the right to live, the right to live, the right to life. So the driver applies the brakes. And you see the driver applying the brakes. So, instinct, you have to put your hands, your arms forward, holding the front seat, holding the seat in front of you, because you already anticipate that from a fast speed to a sudden stop, your body moves forward. Law of inertia, first law of motion. Why it will move forward? Because the first law of motion is telling us a body in motion will continue in motion. That's why in any accident, especially a motorcycle collision, the usual cause of death is head injury, because the mass of your head, okay, according to the executor or executioners during the time of King Henry the Fourth, according to history, there is that penalty there, death penalty by guillotine, putol, liog. And then according to the executioner, according to history, the one I read, that the average mass of the human head is between 8 kilograms and 12 kilograms. So, what part of your body heavier than 8 kilograms? Wala na. So, therefore, your head is the heavier part, or if not the heaviest part of your body, your head. So, it has greater inertia. From a sudden stop, this will move forward. Your head moves forward. So, collision with something hard will be serious to your head. Okay. Okay. So, number 7? Yes, number 7. So, there is that you are asked a question. What is the force? Okay, what is the force? Force here, number 7. Force is equal to F times M times A. Okay? Then, A times A, then, where is that? Okay. Our M here is the mass of the woman. The M, the mass of the woman. Given in the problem, 57 kilograms, the mass of the woman. Acceleration here, the acceleration, okay, is equal to V minus V sub 0 over T. Similar to this equation. Similar to this equation. V is the final speed. A is the initial speed. The initial speed given. What is the initial speed? You look at the book. I will look at the book also. The initial speed is 50 kilometers per hour. 50 kilometers per hour, the initial speed. What is the final speed? V, final speed. What's the final speed? The final speed is 0. Okay? The final speed is 0 because there is collision, and after the collision, the speed is 0. What's the time? Time is given. 0.12 second. So acceleration therefore, okay, you can solve the acceleration. This is equal to 0 minus 50 kilometers per hour. Time here is 0.12 second. The answer here is a negative acceleration. And remember, negative deceleration. Okay, deceleration. Now, you are going to convert this one to meters per second. 50 kilometers per hour equals how many meters per second? Convert that. Apply chapter 1. Okay. Then after converting, you will have the acceleration in meters per second squared. You substitute here for A. How about M? Mass. Mass is already given. 57 kilograms. So, kilogram unit for acceleration. The final unit of the acceleration here, final unit will be meter per second squared. By conversion. The answer is negative. Okay? Negative. And that is expected because in a collision, there is a decreasing speed involved. The speed decreases until it stops. Okay. Okay. So you can solve for number 7. Then number 8. It's number 7, ha? M given 57 kilograms. A acceleration. Okay. Number 8. Number 8. A heavy freight train, a total mass given. Force given. Okay? What is the acceleration? Then what is the, how long will it take? How long will it take to increase the speed from 0 to 50? Okay. We are now on number 8. Number 8, ha? Number 8. I'm going to erase this one. Number 8. I'm going to erase this, erase. Okay. Erase. You just review, review. In the video review. Number 8. This is number 8. Acceleration is being asked F over M. Right? Acceleration is being asked 8 number F over M. What is the acceleration? Second law of motion. A equals F over M. How long? Next question. How long does it take to increase the speed from 0 to 50 kilometers per hour? So, this is the first question. Okay? Then the next question, letter B, the next question, how long you are going to use the equation T, how long? V minus V sub 0 over A. Okay? This equation is derived from this equation. So we'll be using this equation from time to time. Okay. Now, in all the problems, you will be using these equations. In all the problems, you have x minus x sub 0 or from here you have A equals and usually our x sub 0 equals 0. So therefore you will have here this equal to 0. So x equals that. And this one also will be b squared minus v sub 0 squared over 2x. if x equals 0. Now, you will be using these equations in all the problems from 1 to 20, chapter 2. Okay? In most of the problems, not all. In most of the problems. Okay. Now, here, my dear students, there is a calculus involved in problem. Calculus involved in problem. Let me check out. This is problem number 20. Number 20 and number 21. Okay? You just try to solve that. In our previous, in chapter 2, we have also calculus there, integration. Remember, you integrate v dt, a dt. What's that? V dt. Yes, v dt. Okay? Then, you will have here a t dt. In our previous equation, previous problem, chapter 2, you have that, and a is constant, so a t dt. And in problem 20, you will be using derivatives. Okay? So you have number 20. The problem is asking here, a proton moving in an electric field with the equation. So you are asked there. Then you are asked components of the force acting on protons, magnitude of the force. So when you have the force, this is number 20. A here, our A is equal to, our A here is equal to dv dt. It's a vector. Our acceleration is a vector. Now, when you have vector quantities, usually or normally, we employ unit vectors ijk. That's why there is here ijk. Unit vector I, unit vector j, unit vector k. There is an explanation in the book. In this problem, you are given R. Okay? R here, okay, is a displacement. A displacement is a vector quantity. The scalar quantity of a displacement is distance. But because there is ijk involved here, we call this one the displacement. Okay? And therefore, a vector quantity, that's why it involves ijk. Now, our V here, V is equal to dr dt. Then our R is given, so you are going to have the time derivative or ddt of R. R is given with ijk. Now, you try to review, this is a challenge, try to review how the ijk will be solved, and after all the reviews, okay, you try to solve this one. Okay? I'll just give you the final answer. Okay? The final answer for our F, because it is the problem is asking for F, the final answer is something like negative 6.8 or something like, my solution, how to solve this one, 22, 22. 21, 22. Okay. our f here will be vector. Final answer. In this particular problem, the final answer there is negative 6.8 times 10 to the negative 22. Then, the unit vector I was cancelled out in the process. The unit vector I was cancelled out in the process. Then, plus 1.4 times 10 to the negative